In exploring the connections between Quranic themes and modern physics, we've ventured into a dialogue where ancient spiritual insights meet contemporary scientific inquiry. This exploration is not about proving one by the other, but about illustrating how both can enrich our understanding of existence. Awe and wonder. The Quran's repeated calls to reflect on the signs in the heavens and the earth resonate with the scientific pursuit of understanding the universe's mysteries. Both encourage a sense of awe and wonder at creation, whether from a spiritual or scientific perspective. Unity and interconnectedness. The concept of Tawheed, the oneness of God, can inspire the search for a unified theory in physics, suggesting that beneath the apparent complexity lies a profound unity. This unity reflects in the interconnectedness of all things, from the quantum entanglement to the cosmic web of galaxies. Ethical responsibility. The ethical dimensions in the Quran emphasize using knowledge for the betterment of society, a principle that aligns with the ethical considerations in science, particularly in how we apply discoveries like those in particle physics or genetic engineering. The role of humility. Both spiritual teachings and scientific inquiry remind us of the limits of human knowledge. The Quran's acknowledgement of the unseen and the vastness of divine knowledge parallels the humility required in science, where each answer often leads to new questions. Purpose and stewardship. The Quran's depiction of humans as stewards of Earth encourages a responsible approach to scientific exploration, urging us to consider the long-term impacts of our actions on the planet and its inhabitants. Complementarity of knowledge. By seeing science and spirituality not as opposing forces, but as complementary paths to truth, we can foster a worldview where both can coexist, each offering insights into different aspects of the human experience and the nature of reality. Ultimately, this intersection of Quranic philosophy with modern physics invites believers and scientists alike to pursue knowledge with reverence. Whether through prayer, meditation, or experimentation, the quest for knowledge is seen as a noble endeavor when approached with reverence for the mysteries of life and creation. Embrace the mystery. Both the Quran and science acknowledge the vastness of the unknown. This acknowledgement can lead to a more profound appreciation for the universe's complexity and beauty. Live ethically. With great knowledge comes great responsibility. The Quran's ethical teachings can guide scientists in using their knowledge to promote peace, justice, and the well-being of all creation. This dialogue between the Quranic worldview and the scientific exploration of the cosmos doesn't resolve all conflicts or answer all questions, but instead opens new avenues for thought, where each discipline can inform and inspire the other. It's a reminder that in the pursuit of understanding, we are all, in some way, searching for the same truth, albeit through different lenses. Further reflections and implications. Building on the conclusion, here are some additional thoughts on how this dialogue between Quranic teachings and modern physics might shape our approach to life, science, and spirituality. Holistic understanding. Recognizing that both spiritual insights and scientific discoveries offer different but complementary views of reality encourages a holistic approach to knowledge. This can lead to a more integrated understanding of our place in the universe, where the spiritual and material dimensions of life are not seen in opposition, but as parts of a whole. Education and dialogue. This intersection can inform educational practices by promoting curricula that include both scientific literacy and spiritual or ethical education. It encourages educators to foster environments where students can explore the big questions of existence through both empirical evidence and philosophical reflection. Environmental stewardship. The Quranic emphasis on stewardship can inspire environmental science and policy, pushing for sustainability and respect for nature. Understanding the universe's laws through physics can enhance our ability to care for our planet, seeing it as a divine trust. Innovation with integrity. The ethical considerations embedded in Quranic teachings can guide innovation in science and technology, ensuring that advancements serve humanity positively. It suggests a model where scientific breakthroughs are measured not just by their technical prowess, but by their impact on society and ethical considerations. Personal and collective growth. On an individual level, this dialogue can enrich personal growth by encouraging a life where intellectual pursuits are balanced with spiritual practices. Collectively, it can lead to societies that value both the pursuit of knowledge and the cultivation of moral virtues, fostering environments where wisdom, rather than just information, is the goal. The quest for meaning. While science can answer how questions about the universe, the Quran and similar spiritual texts address the why. This partnership can help individuals find meaning in scientific discoveries, seeing them as part of a larger narrative or purpose, thus alleviating the modern existential crisis where science sometimes seems to strip away meaning. Interfaith and interdisciplinary conversations. By drawing parallels between Islamic teachings and scientific principles, we open doors for interfaith dialogue where different religious perspectives can engage with science, potentially finding common ground in the quest for truth and understanding. Respect for mystery. Both the Quran's acknowledgement of the unseen and science's recognition of the limits of current knowledge remind us to respect the mystery of existence. This respect can lead to humility in both scientific and spiritual pursuits, acknowledging that there will always be more to learn and explore. Encouraging curiosity and inquiry. The Quran's invitation to ponder over creation can be seen as an encouragement for scientific curiosity. This can lead to a cultural shift towards valuing inquiry and questioning, seeing them as forms of worship or reverence for the Creator's work. Final thoughts. This exploration does not aim to merge science with religion in a way that dilutes either, but rather to show how they can coexist in a dialogue that enriches human understanding. By seeing the universe through the dual lenses of science and spirituality, we are invited to live with greater awareness, responsibility, and appreciation for the tapestry of existence. In this light, the pursuit of knowledge becomes not just an academic endeavor, but a profound journey towards understanding our place in the cosmos, guided by both the light of reason and the light of faith. The passage you've provided is a comprehensive overview of the evolution of our understanding of elementary particles and the forces of nature, primarily focusing on the historical development of these concepts from ancient Greek philosophy to modern quantum field theory. Here's a breakdown of the key points. Historical context. Aristotle proposed that matter consists of four elements: earth, air, fire, water, acted upon by gravity and levity. Democritus advocated for the concept of atoms as indivisible units, contrasting with Aristotle's continuous matter theory. John Dalton, in 1803, supported the atomic theory by explaining chemical compounds' fixed proportions through molecular structures. Development of atomic theory. Brownian motion. Einstein, 1905, provided evidence for atoms by explaining the random movement of particles in a liquid as collisions with atoms of the liquid. J.J. Thomson, 1897, discovered the electron, suggesting that atoms have internal structure. Ernest Rutherford, 1911, proposed the nuclear model of the atom with a dense, positively charged nucleus and orbiting electrons. Particle physics. Evolution. James Chadwick, 1932, discovered the neutron, showing that the nucleus contains more than just protons. Murray Gell-Mann, 1960s, introduced quarks, proposing that protons and neutrons are composed of quarks, further breaking down the concept of indivisibility. Quarks and forces. Quarks, 6 flavors: up, down, strange, charmed, bottom, top, and 3 colors: red, green, blue. But these terms are labels, not literal colors. Forces. Gravity. Carried by hypothetical gravitons, very weak but long range due to no mass. Electromagnetic force. Carried by photons, strong but balanced in large bodies by equal amounts of positive and negative charges. Weak nuclear force, responsible for radioactive decay, carried by W and Z bosons. Unified with electromagnetism in the Weinberg-Salam theory. Strong nuclear force. Binds quarks into protons and neutrons via gluons, with properties like confinement and asymptotic freedom. Grand unified theories, GUTs, aim to unify the electromagnetic, weak and strong forces at high energies, predicting phenomena like proton decay, which has not yet been observed directly. Philosophical and physical implications. The discussion on matter-antimatter asymmetry explains why the universe might have more matter than antimatter, which could be tied to the weak force's violation of certain symmetries. This narrative illustrates how scientific understanding evolves, often through the integration of new experimental evidence with theoretical frameworks, moving from simplistic ancient models to the complex yet still incomplete picture of particle physics we have today. If you have specific questions about any part of this development or need further clarification, feel free to ask. Neutrino physics is a fascinating area of particle physics that deals with one of the most elusive and weakly interacting particles known to science. Here's an overview. What are neutrinos? Nature. Neutrinos are fundamental particles that belong to the lepton family. They come in 3 flavors corresponding to the charged leptons: electron neutrino, Ne, muon neutrino, Nem, and tau neutrino, Nt. Properties. Mass. Neutrinos were initially thought to be massless, but experiments like those involving neutrino oscillations have shown they have a very small, non-zero mass. Charge. Neutrinos are electrically neutral. Weak interaction. They only interact via the weak nuclear force and gravity, though this interaction is negligible for practical purposes. Neutrino oscillations. Discovery. Neutrino oscillations were first suggested by Bruno Pontecorvo in the 1950s, but were experimentally confirmed much later. This phenomenon implies that neutrinos can change from one flavor to another as they travel, which is possible only if neutrinos have mass. Implications. Mass hierarchy. The study of oscillations helps determine the mass differences between neutrino types, but not their absolute masses. CP violation. There's ongoing research into whether neutrinos and antineutrinos oscillate differently, which could explain the matter-antimatter asymmetry in the universe. Sources of neutrinos. Natural sources, solar neutrinos, produced in the sun's core during nuclear fusion. Atmospheric neutrinos, generated from cosmic rays interacting with Earth's atmosphere. Cosmic neutrinos, from supernovae, active galactic nuclei, and other cosmic events. Artificial sources, nuclear reactors. Neutrinos are produced in beta decay. Accelerators. Particle accelerators can produce neutrinos in controlled experiments. Detection challenges. Due to their weak interaction, detecting neutrinos requires large detectors filled with thousands of tons of material, like water or liquid argon, to observe the rare interaction events. Techniques. Cherenkov radiation. Detectors like Super Kamiokande use water to detect the faint light from particles moving faster than light in water. Scintillation counters. Some detectors use materials that emit light when struck by particles. Bubble chambers, used in older experiments, where charged particles create visible tracks. Major experiments in observatories. Super Kamiokande, Japan. Notable for neutrino oscillation studies. Ice Cube, South Pole. Detects neutrinos from cosmic sources by observing interactions in ice. Camland, Japan. Focuses on reactor neutrinos to study neutrino oscillations. Dune, Deep Underground Neutrino Experiment, USA. Future experiment to study neutrino oscillation with long baseline neutrino beams. Current research and future directions. Mass determination. Experiments like Katrin aim to measure the absolute neutrino mass scale. Sterile neutrinos. There's interest in whether there might be additional, non-interacting sterile neutrinos. Neutrinoless. Double beta decay. If observed, this would confirm that neutrinos are their own antiparticles, Majorana particles, and could explain the matter-antimatter imbalance. Neutrino physics continues to be a key area for both theoretical and experimental physics, with implications for our understanding of the universe, from fundamental particle interactions to cosmology. If you have specific questions about neutrinos or their physics, feel free to ask. Dark matter is one of the most intriguing and mysterious aspects of modern cosmology and particle physics. Here's an overview of the current understanding and theories regarding dark matter particles. What is dark matter? Definition. Dark matter is an inferred substance that does not emit, absorb, or reflect light, making it invisible in the electromagnetic spectrum. However, its presence is deduced from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Evidence: galactic rotation curves. Stars and galaxies orbit at speeds that suggest there's more mass than what's visible. Gravitational lensing. Light from distant galaxies is bent by dark matter, indicating mass presence where no visible matter exists. Cosmic microwave background. The patterns in the CMB suggest dark matter's role in the early universe. Theoretical candidates for dark matter particles. Here are some of the leading particle candidates for dark matter. Weakly interacting massive particles, WIMPs. Properties. These are hypothetical particles that interact through gravity and the weak nuclear force, but not electromagnetically. They are thought to have masses from a few GeV to several TeV. Detection. Experiments like ELUX, Exanon, and SuperCDMS aim to detect WIMPs through direct detection in underground labs where cosmic radiation is minimal. Axions and axion-like particles, ALPs. Properties. Proposed to solve the strong CP problem in quantum chromodynamics. Axions are very light, sub-eV, and would interact very weakly with normal matter, potentially through their coupling to photons. Detection. Searches involve looking for actions converting into photons in strong magnetic fields, e.g. the ADMX experiment. Sterile neutrinos. Properties. Hypothetical neutrinos that do not interact via the weak force, only through gravity. They could have masses in the keV range, fitting models for dark matter in galaxy halos. Detection. Indirect detection via X-ray emissions from their decay or through cosmic microwave background anomalies. Self-interacting dark matter, SIDM. Concept. Dark matter particles that can interact with each other, but not significantly with baryonic matter. This could explain certain galactic structures like cores in dwarf galaxies. Primordial black holes, PBHs. Idea: very small black holes formed in the early universe could constitute part or all of dark matter. Their detection would be through gravitational effects, or potentially through their Hawking radiation if very small. Other exotic candidates: supersymmetric particles, SUSY. If supersymmetry is realized in nature, some supersymmetric particles could be WIMP-like dark matter candidates. Asymmetric dark matter. Analogous to the baryon asymmetry in the universe, this posits that there might be an asymmetry between dark matter and anti-dark matter. Challenges and future directions. Detection. The direct detection of dark matter particles remains elusive. The lack of confirmed signals from experiments like those searching for WIMPs has led to revising the expected properties of dark matter or exploring alternative candidates. Cosmological constraints. New data from CMB observations, galaxy surveys, and gravitational lensing continue to refine the constraints on dark matter properties and its distribution. Theoretical developments. Advances in particle physics theory, like those in string theory or modified gravity theories, might offer new candidates or even challenge the need for dark matter. Next-generation experiments. Future experiments aim to increase sensitivity or explore different detection techniques, such as looking for dark matter annihilation signals in space with telescopes like Fermi-LAT, or through large-scale experiments like the upcoming Simons Observatory. Dark matter continues to be a frontier in physics, driving both theoretical and experimental efforts to understand what constitutes a significant portion of the universe's mass energy content. If you have more specific questions about dark matter or related physics, feel free to ask. The concept of dark matter is a modern scientific theory that was not known during the time the Quran was revealed. Therefore, any suggestion that the Quran explicitly mentions or describes dark matter would be an interpretation rather than a direct translation or explicit mention. However, some scholars and enthusiasts have made connections between certain verses from the Quran and contemporary scientific concepts like dark matter. Here are some interpretations based on the search results you provided. Quranic verses suggested to relate to dark matter. Surah 21:16, 38:66, 26:24, 26:28, 1965, 38, 1585. These verses collectively use the phrase wa ma bainahum, which translates to all that is between them. Some interpretations suggest that this could refer to the unseen elements or forces like dark matter, which hold the universe together. For example, the interpretation given in one result posits that dark matter is holding the universe together. And this is inferred from these verses. Surah Al-Haqqa 69:38-39. This verse, "But nay, I swear by all that ye see, that it is indeed the speech of an illustrious messenger," has been interpreted by some to imply the existence of matter or phenomena that are not visible, which could metaphorically relate to dark matter. Interpretation and context. These interpretations are not universally accepted among Islamic scholars and are often seen as speculative or metaphorical readings of the text to align with scientific discoveries. The Quran primarily deals with spiritual guidance, moral principles, and divine laws, and its verses are often open to multiple interpretations. Scientific and religious discourse. Discussions around these interpretations often aim to highlight the compatibility between Islamic teachings and modern science. However, they are not considered scientific evidence or authoritative interpretations of the Quran in terms of cosmology or physics. Scholarly caution. Islamic scholarship generally advises caution in equating Quranic verses directly with modern scientific discoveries without clear textual or historical justification. The Quran is not a scientific textbook, but a book of guidance, and interpretations that directly link its verses to scientific phenomena are often debated for their validity. In summary, while some individuals argue that certain verses in the Quran could be interpreted to hint at concepts like dark matter, these interpretations are not conclusive or universally accepted within Islamic scholarship. They reflect personal or cultural interpretations rather than direct references to modern scientific concepts. Islamic cosmology refers to the cosmological views within Islamic theology, philosophy, and science, which have evolved significantly over time. Here's an overview of Islamic cosmology from its classical forms to the influences and interpretations of modern science. Classical Islamic cosmology. Quranic cosmology. The Quran describes the creation of the heavens and the earth, the sun, moon, and stars, often in a way that emphasizes their signs, ayat, for reflection and understanding of God's omnipotence. Creation of the universe. Verses like 21:30 suggest the universe was created from a single mass, smoke, or a singularity, which then was separated. Seven heavens. The concept of seven heavens, e.g., 229, is prevalent, interpreted in various ways, from literal layers to metaphorical states of existence. Medieval Islamic astronomy. Geocentric model. Like their contemporaries in Europe, Muslim astronomers initially adhered to a Ptolemaic geocentric model, where Earth was at the center with celestial bodies revolving around it. Al-Battani and Al-Biruni. These scholars refined astronomical observations, contributing to the accuracy of planetary motions and the calendar. Philosophical perspectives. Al-Kindi, Al-Farabi, Ibn Sina, Avicenna, and Ibn Rushd, Averroes, contributed to cosmological thought by integrating Aristotelian philosophy with Islamic theology, discussing issues like the eternity of the world versus its creation, the nature of the heavens, and the interplay between divine will and natural law. Islamic cosmology and modern science. Reconciliation with modern cosmology. Expansion of the universe. Some interpretations of verses like 51:47, "And the heaven we constructed with strength, and indeed, we are its expander," have been linked to the modern concept of the expanding universe. Big Bang theory. The idea of a singular origin or smoke in Quranic descriptions has been associated by some with the Big Bang, though this is more of an interpretative analogy. Dark matter and dark energy. As mentioned, some draw connections between all that is between them in various verses and modern scientific concepts like dark matter, though these are not direct references but rather speculative interpretations. Islamic scholars and modern science. Mahmoud Hessabi and Ziauddin Sardar, among others, have worked on reconciling Islamic thought with modern science, often advocating that Islamic teachings are not in conflict with scientific discovery, but rather encourage scientific inquiry as part of understanding God's creation. Contemporary views. Diverse interpretations. Today, Islamic cosmology encompasses a wide range of views. Literalists might adhere strictly to traditional interpretations of the Quran and Hadith. Rationalists or modernists might interpret cosmic descriptions in the Quran metaphorically or symbolically, allowing for compatibility with scientific understanding. Scientists with Islamic backgrounds often separate their scientific work from religious beliefs, focusing on empirical evidence while respecting the spiritual dimensions of their faith. Theological implications. Discussions often revolve around how to understand God's role in an expanding universe, the purpose of life in light of cosmic scale, and how to interpret divine attributes like omniscience and omnipotence in relation to the laws of physics. Challenges and debates. Science versus religion. There's an ongoing debate on how much one should interpret religious texts through the lens of modern science, with some arguing for a clear separation, while others see science as a path to understand God's creation more deeply. Cultural and educational impact. In many Muslim-majority countries, the integration of modern science into educational curriculums while respecting religious beliefs remains a nuanced challenge. Islamic cosmology, therefore, is not a monolithic concept, but a dynamic field where traditional beliefs intersect with contemporary scientific understanding, leading to rich discussions and interpretations within Islamic scholarship and beyond. The concept of the seven heavens in Islam is derived from several verses in the Quran, which mention this structure in various contexts. Here's a breakdown of how it's interpreted within Islamic theology, philosophy, and contemporary thought. Quranic references. The Quran mentions the concept of seven heavens in several verses. 2:29. He it is who created for you all that is in the earth. Then turned he to the heaven and fashioned it as seven heavens, and he is knower of all things. 65:12. Allah it is who hath created seven heavens, and of the earth the like thereof. The commandment cometh down among them slowly, that ye may know that Allah is able to do all things, and that Allah surroundeth all things in knowledge. 71:15. See ye not how Allah hath created seven heavens in harmony? Classical interpretations. Literal interpretation. Physical layers. Some traditional scholars have interpreted these heavens as literal physical layers, each with its own celestial bodies, angels, and specific functions or characteristics. For instance, each heaven might have its own firmament or sky. Spiritual or metaphysical interpretation, levels of paradise. Another interpretation sees the seven heavens as layers of paradise, Jannah, where different levels of reward await believers based on their deeds and faith. Realms of existence. Philosophers like Al-Ghazali and Ibn Arabi saw these heavens as stages of spiritual or metaphysical progression towards God, representing different dimensions of existence or states of being. Symbolic interpretation. Symbolic of perfection. The number 7 often symbolizes completeness or perfection in Islamic numerology. Therefore, the seven heavens might symbolize the perfect, complete order of the universe, or the comprehensive nature of divine creation. Philosophical and Sufi views. Cosmological order. In Islamic philosophy, particularly among figures like Ibn Sina, Avicenna, the heavens might represent the celestial spheres, each managed by an intellect or angel, aligning with Aristotelian cosmology, but adapted into Islamic theology. Sufi perspective. In Sufism, the journey through the seven heavens can be seen as a metaphor for the spiritual ascent towards God, with each heaven representing a stage of purification and enlightenment. Modern interpretations. Scientific compatibility. Astronomical layers. Some modern interpretations attempt to reconcile the seven heavens with astronomical knowledge, suggesting these could refer to layers of the atmosphere, planets, or even galaxies, though this is more metaphorical than literal. Metaphorical understanding, layers of knowledge or reality. Another contemporary view might treat the seven heavens as symbolic of different levels of understanding or realms of reality, both physical and metaphysical, that human beings can explore or comprehend. Cultural and educational context. In educational and cultural discussions, the concept might be taught as part of Islamic cosmology, emphasizing the awe and wonder of God's creation, while also encouraging scientific curiosity. Challenges and discussions. Interpretation versus science. There's an ongoing discussion on how to interpret these verses in light of modern science. Literal interpretations might clash with scientific understanding, leading to debates on whether these descriptions should be seen as allegorical or symbolic. Diversity in thought. Interpretations can vary widely, from those who see it strictly in religious terms to those who seek a synthesis with scientific understanding, reflecting the diversity within Islamic thought. The concept of the seven heavens in Islam, therefore, offers a rich tapestry of interpretations, balancing between the literal, the symbolic, and the spiritual, inviting believers to ponder the vastness and complexity of creation. The concept of seven earths in Islam is less commonly discussed compared to the seven heavens, but is still referenced in Islamic texts, particularly in the Quran and Hadith. Here's an exploration of how this concept is understood. Quranic reference Quran 65:12. Allah is He who created seven heavens, and of the earth the like thereof. His command descends between them, that you may know that Allah is able to do all things, and that Allah surrounds all things in His knowledge. This verse suggests a parallelism between the heavens and the earths, indicating that just as there are seven heavens, there are seven earths. Interpretations. Literal interpretation. Physical earths. Some classical scholars have interpreted this to mean there are literally seven different earths or planets, each possibly inhabited. This view might be seen as an early form of acknowledging the existence of other worlds or planets, though it's not widely held in modern times due to scientific understanding. Symbolic or metaphysical interpretation. Layers or dimensions of Earth. Similar to the interpretation of the heavens, the seven earths could symbolize different layers or dimensions of the physical Earth or different realms of existence within it. This might include different geological layers, or metaphorically, different aspects of human experience or spiritual states. Cosmological and eschatological view, stages of creation. The seven earths might represent stages in the creation process, or conditions of the earth across different epochs or during the Day of Judgment, when the earth undergoes transformations. Sufi perspective, spiritual realms. In Sufism, this concept could be extended to mean seven levels of spiritual or existential planes one must traverse in the journey towards divine knowledge or unification with the divine. Hadith and other Islamic texts. Hadith narrations. There are several hadiths that discuss the seven earths, often describing them in more detail. A hadith in Sahih Muslim mentions that below the earth there are seven earths, each with its own inhabitants, differing in forms and sizes. Another narration describes each earth having a prophet like Adam in our world, suggesting a parallel in creation across these earths. Tafsir, exegesis. Scholars like Ibn Kathir in his tafsir of the Quran discuss these verses, often leaning towards a more metaphorical or symbolic understanding, emphasizing the omnipotence and vastness of God's creation. Modern interpretations. Compatibility with science. Contemporary approaches might interpret the seven earths metaphorically to align with scientific understanding of the Earth's structure, like the crust, mantle, core, or even the solar system's planets. However, these interpretations are more about finding harmony than literal translation. Educational and cultural context. In modern Islamic education, the focus might be on the awe of creation and the encouragement of scientific inquiry, rather than insisting on a literal interpretation of seven physical earths. Challenges and discussions. Science versus religious text. The concept poses a challenge when trying to reconcile religious texts with scientific knowledge. While some see no need for literal interpretation, others might struggle with how to integrate these descriptions into a modern worldview. Diversity of thought. Like many Islamic concepts, interpretations can vary widely. from the literal to the deeply symbolic, reflecting the diversity within Islamic scholarship and practice. In summary, the 7 Earths in Islam serves as a concept that invites contemplation on the vastness of creation, the layers of understanding or existence, and the sovereignty of God, with interpretations ranging from the literal to the profoundly symbolic. The concept of 7 Earths in Islamic literature is notably mentioned in several hadiths, which are part of the broader Islamic tradition. Here are some key hadiths that relate to this concept. Sahih Muslim. One of the most cited hadiths regarding the 7 Earths comes from Sahih Muslim. Hadith number 2956, or similar numbering depending on the edition of Sahih Muslim. The Prophet Muhammad is reported to have said, "When Allah created the earth, it was one earth. He then divided it into 7 Earths. Between the first earth and the one beneath it, there is a distance of 500 years, and between each earth and the one beneath it, there is a distance of 500 years. This hadith then describes the inhabitants of each earth, mentioning that each has its own Adam, its own prophet, and its own inhabitants with varying forms and sizes. Other hadiths. Sunan al-Tirmidhi, hadith number 3354. Allah created 7 Earths. In each earth there is an Adam like your Adam, a prophet like your prophet, and everything like what you have on earth. Musnad Ahmad ibn Hanbal, volume 3, hadith no. 14783. A similar narration where the Prophet speaks about 7 Earths, each with its own inhabitants and characteristics. Interpretations of these hadiths. Literal interpretation. Some scholars take these hadiths at face value, suggesting the existence of multiple physical Earths or planets, each with its own life forms, possibly hinting at an early Islamic acknowledgement of a universe filled with life. Symbolic or metaphysical interpretation. Layers of existence. The 7 Earths might symbolize different layers or realms of existence, not necessarily physical, but perhaps spiritual or metaphysical layers of creation or human experience. Moral or spiritual levels. They could also represent different levels of spiritual or moral development, where each Earth might symbolize a stage in the journey towards God or moral perfection. Sufi interpretations. In Sufism, these Earths are sometimes seen as stages of spiritual purification or enlightenment, where the journey through each Earth represents an ascent in spiritual awareness. Challenges in modern context. Scientific understanding. Modern science doesn't support the existence of 7 physical Earths in our current understanding of the cosmos. Therefore, literal interpretations might be at odds with scientific knowledge, leading to more symbolic or metaphorical readings. Educational and scholarly context. Islamic scholars and educators often emphasize the metaphorical or allegorical nature of these descriptions, focusing on the lessons about the vastness of Allah's creation and the encouragement of curiosity about the universe. Diverse views. Within Islamic scholarship, there's a range of interpretations. Some might treat such hadiths as allegories for the diversity of creation or the multifaceted nature of existence, while others might see them as a call to ponder the infinite wisdom of God. Conclusion. The hadiths on the 7 Earths provide a fascinating insight into Islamic cosmology, inviting believers to reflect on the enormity and diversity of creation. Whether interpreted literally, metaphorically, or eschatologically, these narrations underscore the theme of divine majesty and the complexity of the universe as understood in Islamic thought. Sufi interpretations of Islamic concepts, including those related to cosmology like the 7 heavens and 7 Earths, are deeply spiritual and often metaphorical, focusing on the inner journey of the soul towards divine unity. Here's how Sufis might interpret these concepts. 7 heavens. Stages of spiritual ascent. In Sufism, the 7 heavens are seen as stages or stations, maqamat, on the spiritual path towards God. Each heaven could represent purification, tazkiyah. The first step involves purification of the self from worldly desires and sins. Repentance, tawbah, acknowledging and turning away from past mistakes. Patience, sabr, enduring trials with patience, seeing them as opportunities for growth. Gratitude, shukr, thankfulness for God's blessings, which opens the heart further. Trust, tawakkul, Complete reliance on God, where one's ego diminishes. Love, mahabba, a profound love for God that begins to dominate one's life. Union, ittihad, the final stage where the mystic experiences unity with the divine, though this is more a state of consciousness than literal unity. Spiritual realms. Each heaven might also symbolize different realms of existence or states of consciousness where the soul encounters various divine attributes, leading to a deeper understanding of God. 7 Earths levels of spiritual descent. While the heavens are about ascent, the earths can represent the descent or journey through different aspects of the self or material existence. The physical realm. The first earth might symbolize the physical world where one begins their spiritual journey. The psychological realm, dealing with one's psyche, desires, and ego. The emotional realm, navigating through emotions, attachments, and detachments. The intellectual realm, engaging with knowledge, wisdom, and the discernment between truth and illusion. The moral realm, testing one's ethical conduct and moral integrity. The social realm, interactions with others, reflecting one's spiritual state through acts of kindness, justice, and compassion. The mystical realm, the deepest layer where one confronts the essence of their being, leading to spiritual rebirth. Symbol of trials. Each earth might represent different trials or tests that the soul must pass through to purify itself, much like the trials faced by prophets in Islamic tradition. Key Sufi concepts in interpretation, annihilation, fana, and subsistence, baka. The journey through these heavens and earths often culminates in the annihilation of the ego, fana, followed by subsistence in God, baka, where one's identity merges with the divine. Unity of existence, wahdat al-wujud. Influenced by Ibn Arabi, some Sufis interpret the multiplicity of heavens and earths as manifestations of the one divine reality, where all distinctions are ultimately illusory. Symbolism. Sufis are known for their use of symbolic language. The numbers, like 7, often symbolize completeness or perfection, and the journey through these layers is a metaphor for the soul's quest for divine knowledge and love. Personal experience. Sufi interpretations are not just intellectual, they are experiential. Each heaven or earth might be understood through personal spiritual experiences, dreams, visions, or meditative states. Modern Sufi thought integration with science. Some modern Sufi thinkers might interpret these concepts in light of contemporary science, seeing them as symbolic of the different planes of reality or consciousness that science is beginning to explore through quantum mechanics or psychology. Cultural and universal application. While rooted in Islamic theology, Sufi interpretations often transcend strict religious boundaries, offering insights into the human condition and spiritual life universally. Sufi interpretations thus transform cosmological concepts into a profound spiritual journey, focusing on the inner transformation and enlightenment of the individual soul, seeing the external universe as a reflection of internal spiritual landscapes. Sufi cosmology is a blend of mystical interpretations and traditional Islamic views on the nature of the universe, focusing on the spiritual dimensions of existence. Here's an exploration of key aspects. Fundamental concepts. Unity of being, wahdat al-wujud. Perhaps the most central idea in Sufi cosmology, particularly in the thought of Ibn Arabi, this concept suggests that all existence emanates from and is ultimately one with the divine essence. Everything in the universe is a manifestation of God, and distinctions are only apparent, not real. Cosmic hierarchy. Sufism often sees the universe in a hierarchical order, where the divine. At the top is God, the Absolute, from whom all things emanate. The intelligences or spirits. Below are various levels of spiritual entities or intelligences, often corresponding to the angels in traditional Islamic cosmology, but with a more esoteric role in mediating between the divine and the material. The soul. Human souls are seen as divine sparks or breaths from God, traveling through various planes of existence. The material world. The lowest level, where the physical universe resides, is considered a place for the soul's journey and purification. The universe as a mirror. Microcosm and macrocosm. Sufis often use the analogy of the human being as a microcosm, reflecting the macrocosm, the universe. The inner journey of the soul mirrors the cosmic journey, suggesting that understanding oneself is key to understanding the cosmos. Symbolism in nature. Natural phenomena are often seen as signs, ayat, or symbols of divine truths. For example, the sun might symbolize the divine light, and the night sky, the vastness of divine knowledge. Spiritual geography, the seven heavens and earths. As previously discussed, these might represent stages of spiritual ascent or descent, but in Sufi cosmology, heavens are stages of purification, enlightenment, and closeness to God. Earths symbolize different layers of human experience or spiritual trials one must pass through. Alam al-Mithal, the world of imagination, or imaginal world, a realm between the physical and the purely spiritual, where forms and ideas exist in a more concrete way than in the purely intellectual realm. This is where visions, dreams, and mystical experiences occur, blending the inner and outer realities. Cosmic journey. Spiritual ascension. Miraj. The Prophet Muhammad's night journey, Isra and Miraj, is often taken as a paradigm for the spiritual journey every soul can undertake. This journey through heavens represents the soul's travel from the material to the spiritual, from the known to the divine unknown. The path of return. Sufism speaks of an original state of unity with God from which all souls come, and the purpose of life is to return to this state through spiritual practices, love, and knowledge. Gnosis. Sufi practices and cosmology. Dhikr, remembrance. Through remembrance of God, one aligns oneself with the cosmic rhythm, seeing all creation as a manifestation of divine names and attributes. Meditation and contemplation. Sufi meditation often involves contemplating the cosmos as an expression of divine unity, leading to insights into one's own nature and the nature of reality. Music and poetry. In many Sufi traditions, music, sama, and poetry are used to transcend the material, connecting the heart to higher realities, reflecting the cosmic harmony. Modern interpretations. Integration with science. Some contemporary Sufi scholars draw parallels between Sufi cosmology and modern physics, especially in terms of quantum mechanics' concept of interconnectedness or the holographic universe theory, where every part contains the whole, akin to Wahdat al-Wujud. Universal spirituality. While rooted in Islam, Sufi cosmology often speaks in a language that transcends religious boundaries, focusing on universal themes of love, unity, and the journey of the soul. Sufi cosmology, therefore, is not just about the physical universe, but is deeply concerned with how the cosmos reflects and interacts with the spiritual journey of the individual, emphasizing that understanding the external world is intrinsically linked to understanding the inner self and ultimately, the divine. Ibn Arabi, often referred to as Muhyiddin, reviver of religion, or Al-Sheikh al-Akbar, the greatest master, is one of the most influential figures in Islamic mysticism, Sufism. His teachings, encompassing a vast range of philosophical, mystical, and theological insights, have shaped much of Sufi thought. Here are some key aspects of Ibn Arabi's teachings. Unity of being, Wahdat al-Wujud. Core concept. Perhaps Ibn Arabi's most famous doctrine is the unity of being, or oneness of existence. This principle asserts that all existence is a manifestation of the divine essence. There is no true separation between God and creation. All distinctions are relative and ultimately illusory. Implications. This leads to the understanding that every being and phenomenon is a sign, ayat, of God, reflecting His attributes. Humans, in particular, are seen as mirrors of the divine, capable of reflecting all divine names and qualities. Divine names and attributes. Theophany. Ibn Arabi teaches that God manifests himself through his names and attributes. The cosmos is an endless theophany, where every aspect of existence reflects one or more of God's 99 names, or infinite names, according to some interpretations. Human role. Humans are unique in their ability to reflect all names, thus having the potential for a comprehensive spiritual journey where they can experience all aspects of divinity. The perfect man. Al-Insan al-Kamil. Concept. Ibn Arabi elaborates on the idea of the perfect man who embodies the totality of divine attributes. This figure is not just a historical or religious personality, but a metaphysical archetype that every human can strive to realize within themselves. Manifestation. The Prophet Muhammad is often seen as the prime example of Al-Insan al-Kamil, but the concept also includes the potential for every individual to achieve this state through spiritual perfection. Imaginal world. Alam al-Mithal. Intermediate realm. Ibn Arabi speaks of an imaginal world that exists between the physical and the purely spiritual. This is not merely a realm of fantasy, but a place where spiritual realities take on forms perceivable by the soul, where symbolic visions and mystical experiences occur. The journey of the soul. Spiritual ascent. His works describe the soul's journey through various stages or stations, maqamat, and states, awal, reflecting the inner spiritual journey towards God. Annihilation, fana, the dissolution of the ego or self in the divine. Subsistence, baka. After annihilation, the soul subsists in God, maintaining its individuality while fully immersed in divinity. The concept of love. Divine love. Love is central to Ibn Arabi's teachings, seen as the force that binds the cosmos and the primary motivator for the soul's journey back to its origin. Love for God is not merely an emotion, but a transformative power leading to union with the divine. Scriptural interpretation. Symbolic reading. Ibn Arabi encouraged reading the Quran and Hadith not just literally, but symbolically, interpreting them in light of mystical truths. This approach has led to rich, sometimes controversial interpretations of Islamic texts. Cosmology. Macrocosm and microcosm. He saw the universe as a reflection of God's attributes, with every part of creation containing the whole, much like a hologram. This mirrors his idea of the human soul as a reflection of the cosmos and God. Influence and controversy. Legacy. His teachings have inspired countless Sufi poets, scholars, and mystics, but have also been the subject of controversy due to interpretations that some traditionalists see as too radical or pantheistic. Universal application. While deeply Islamic, his philosophy speaks to universal spiritual themes, influencing thinkers and spiritual seekers across various traditions. Ibn Arabi's works, notably Fusus al-Hikam, The Bezels of Wisdom, and Al-Futuhat al-Makkiyah, The Meccan Revelations, are vast and complex, requiring deep study for full appreciation. His teachings continue to be a subject of scholarly interest in spiritual practice, offering insights into the nature of reality, the divine, and the human soul's potential. Unity of being, wahdat al-wujud, is a central and profound concept in Islamic mysticism, particularly associated with the teachings of Ibn Arabi, but also echoed by other Sufi thinkers. Here's a detailed exploration of this doctrine, definition, and core idea. Wahdat al-wujud translates as unity of being, or oneness of existence. It suggests that there is only one true existence, which is the existence of God, and everything else is a manifestation or reflection of this single divine reality. Non-dualism. This doctrine posits a non-dualistic view of existence, where the apparent multiplicity of the world is seen as a temporary or illusionary separation from the divine unity. Philosophical and theological implication. Divine immanence. Everything in existence is an expression of divine attributes. Each creature reflects at least one of the divine names, and humanity, in particular, can reflect all names, embodying the potential for divine manifestation in its completeness. Transcendence and immanence. Despite the immanence, God's essence remains transcendent, beyond all comprehension or comparison. The unity of being does not mean that creation is identical to God in essence, but that all existence is dependent on and derives from God's existence. Interpretation and practice. Spiritual experience. The realization of Wahdat al-Wujud is typically understood as an experiential truth that comes through spiritual practices like meditation, dhikr, remembrance of God, and mystical experiences. It's about moving from intellectual knowledge to a lived understanding of unity. Levels of reality. Ibn Arabi describes different levels or stations of existence where this unity is progressively realized. The world of absolute unity, ahadiyya. The ultimate reality where only God exists. The world of relative unity, wahidiyya, where distinctions exist but are still recognized as manifestations of the One. Human role. Humans play a unique role in this cosmology as they can consciously strive to realize this unity through spiritual purification and knowledge, aiming to become the perfect man, al-insan al-kamil, who embodies all divine attributes. Controversies and misunderstandings. Pantheism versus panentheism. Critics have sometimes accused proponents of Wahdat al-Wujud of pantheism, suggesting that they equate creation with the Creator. However, adherents argue it's more akin to panentheism, where God is both transcendent and immanent, encompassing all creation while remaining distinct from it. Theological debate. This doctrine has been both celebrated and criticized within Islamic scholarship. Some traditionalists argue it blurs the line between the Creator and creation too much, potentially leading to theological errors. Influence and legacy. Sufi orders. Many Sufi orders have been influenced by this concept, particularly those in the Naqshbandi, Qadiri, and Shadili traditions, where it has shaped practices aimed at the realization of divine unity. Literature and art. The idea has penetrated deeply into Sufi poetry, literature, and art, inspiring works that explore themes of divine love, unity, and the dissolution of the self in the divine. Interfaith dialogue. Wahdat al-Wujud has also found resonance in interfaith dialogues, offering a mystical perspective on unity that transcends religious boundaries, akin to concepts in other traditions like Advaita Vedanta in Hinduism. Modern interpretations. Contemporary relevance. In modern times, scholars and spiritual seekers have revisited this doctrine, often interpreting it in ways that resonate with contemporary philosophical and scientific ideas about the interconnectedness of all things, such as in quantum physics or ecological thought. Educational role. It's taught not just for its theological implications, but as a profound philosophical and spiritual outlook that encourages peace, tolerance, and a deeper understanding of the oneness of creation. Wahdat al-Wujud challenges one to look beyond the apparent multiplicity of the world to see the underlying unity, offering a transformative vision of existence where every particle of the universe is a manifestation of the divine. Advaita Vedanta is one of the most influential schools of Vedanta philosophy within Hinduism, known for its non-dualistic Advaita interpretation of the ultimate reality. Here's an overview of its key principles, philosophers, and influence. Core principles: non-dualism, Advaita. Advaita Vedanta asserts that there is no fundamental distinction between the individual soul, Atman, and the ultimate reality, Brahman. The apparent multiplicity of the world is due to ignorance, avidya or maya, and the ultimate truth is that all is Brahman. Brahman, the single, undifferentiated, unchanging, infinite, immanent, and transcendent reality. Brahman is described as Sat Chit Ananda, existence, consciousness, bliss. Atman, the true self or soul, which is identical with Brahman. The individual self, when stripped of all layers of ignorance, realizes it is not separate from Brahman. Maya, often translated as illusion, Maya is the power that veils the true nature of Brahman, leading to the perception of the world as separate and diverse. This isn't to say the world is unreal, but that its separateness is not the ultimate truth. Ignorance, avidya, the root cause of the cycle of birth and rebirth, samsara. Liberation, moksha, comes with the removal of this ignorance through knowledge, jnana. Philosophers Adi Shankaracharya, 788 to 820 CE. The most prominent exponent of Advaita Vedanta, Shankaracharya wrote detailed commentaries on the principal Upanishads, the Bhagavad Gita, and the Brahma Sutras, systematizing Advaita Vedanta. His doctrine includes 3 levels of reality: pragmatic, vyavaharika, apparent, pratipasika, and absolute, paramarthika. Neti, not this, a method of understanding Brahman by negating all that is not Brahman. Other notable figures: Gaudapada, considered Shankaracharya's guru's guru, with his Karika on the Mandukya Upanishad; Vidyaranya and Vachaspati Mishra for their further developments and commentaries. Spiritual practices: Jnana Yoga, the path of knowledge, which involves self-inquiry, Atma Vichara, to realize one's true nature as Brahman. Key practices include Shravana, listening to teachings; Manana, reflecting on them; and Nididhyasana, meditating on the truth of these teachings. Bhakti. Despite being a jnana-oriented philosophy, devotion to a personal deity can also be a path to realize the non-dual truth, as the true object of devotion is ultimately Brahman. Influence and legacy. Cultural impact. Advaita Vedanta has deeply influenced Indian culture, philosophy, and spirituality. It has shaped not only Hindu thought, but also had impacts on Buddhism, Jainism, and Sikhism in their philosophical developments. Modern interpretations. Figures like Swami Vivekananda and Ramana Maharshi have popularized Advaita in the modern era, making it accessible through their teachings and writings. Vivekananda introduced Vedantic ideas to the Western world, and Maharshi focused on self-inquiry, interfaith, and philosophical discourse. Its non-dualistic approach has made it a point of convergence for comparative religion and philosophy, finding parallels with Western mysticism, Buddhism, and even some aspects of modern science and psychology. Contemporary relevance. Advaita continues to be a subject of study and practice, influencing fields like psychology, Nichiji, in concepts related to the self in Jungian psychology, philosophy, and even quantum mechanics, where the idea of an interconnected reality resonates. Challenges and criticisms. Interpretation of Maya. Some critics argue that Advaita's view of the world as Maya, illusion, can lead to a devaluation of the physical world and life experience. Practical ethics. There's debate on how Advaita Vedanta's focus on liberation through knowledge translates into ethical living, although Shankaracharya himself wrote on Dharma. Dualistic schools. Other Vedanta schools like Dvaita, dualism, by Madhva, and Vishishtadvaita, qualified non-dualism, by Ramanuja, offer contrasting views on the relationship between soul, God, and the world. Advaita Vedanta invites one to recognize the unity of all existence beyond the apparent diversity, challenging individuals to transcend ego and realize their true divine nature. Here's a comprehensive overview of elementary particles and the fundamental forces of nature, explained in a structured manner. Elementary particles. Elementary particles are the most fundamental units of matter, considered indivisible based on current understanding. They are categorized into 2 main groups: fermions, quarks; types, flavors, up, down, charm, strange, top, and bottom. Properties: carry fractional electric charges, interact via all 4 fundamental forces, and combine to form hadrons, protons, and neutrons. Colors: each flavor comes in 3 colors: red, green, blue, a concept from quantum chromodynamics, QCD, not literal colors. Leptons: types, electron, E, muon M, tau, T, and their associated neutrinos, N, E, N, M, N, T. Properties: only interact through the weak force and electromagnetism for charged leptons, with neutrinos being nearly massless and interacting only through the weak force. Fermion's role. Fermions are the building blocks of matter. They obey the Pauli exclusion principle, meaning no 2 fermions can occupy the same quantum state simultaneously, which is crucial for atomic structure and the stability of matter. Boson's gauge. Bosons. Photon. G. Carries the electromagnetic force. Gluon. Gibri. Mediates the strong nuclear force, binding quarks within protons and neutrons and holding nuclei together. W and Z. Bosons. W+, WU, Z0. Responsible for the weak nuclear force, involved in processes like nuclear decay. Graviton. Hypothetical particle proposed to mediate gravity, not yet observed. Higgs. Boson. Function. Gives particles mass through the Higgs mechanism, where particles interact with the Higgs field. Boson's role. Bosons are force carriers or mediators. Unlike fermions, multiple bosons can occupy the same quantum state. Fundamental forces. The interactions between particles are governed by four fundamental forces: gravitational force, strength, weakest of the four forces at the particle level, but significant on astronomical scales. Range, infinite, decreases with the square of distance. Particle, hypothetical graviton. Electromagnetic force, strength, much stronger than gravity but can cancel out due to opposite charges. Range, infinite, mediated by photons. Interaction, acts on charged particles, responsible for phenomena like electricity, magnetism, and light. Weak nuclear force, strength, intermediate, much weaker than electromagnetism, but responsible for radioactive decay. Range, very short, about 10^18 meters, mediated by W and Z bosons. Interaction, involved in processes like beta decay where particles change type. Strong nuclear force, strength, strongest of all forces at short distances, binding quarks within protons and neutrons. Range, also very short, mediated by gluons. Interaction, keeps nuclei stable by overcoming the electromagnetic repulsion between protons. Theoretical frameworks. Quantum field theory, QFT, describes particles as excitations of underlying fields, unifying quantum mechanics with relativity for three of the forces: electromagnetic, weak, and strong. Standard model, a theory that encapsulates our understanding of elementary particles and three of the fundamental forces, excluding gravity. It includes electroweak theory, unifying electromagnetism and weak force. Quantum chromodynamics, dealing with the strong force. Grand unified theories, GUTs, attempt to unify the strong, weak, and electromagnetic forces at high energies. String theory, a theoretical framework in which particles are not point-like, but rather one-dimensional strings, potentially unifying all forces, including gravity. Current challenges and research. Dark matter and dark energy. Understanding these mysterious components of the universe, possibly involving new types of particles or forces beyond the standard model. Neutrino mass. Explaining why neutrinos have mass, which is outside the original standard model. Unification of forces. The dream of a theory of everything that includes gravity, potentially through supersymmetry or string theory. Experimental physics. Particle accelerators like the LHC, Large Hadron Collider, continue to probe for new particles or validate theoretical predictions. This explanation provides a snapshot of our current understanding, which is subject to refinement as new experiments and theories emerge. The Quran, while not a scientific textbook in the modern sense, does contain descriptions of the natural world that some interpret in light of contemporary science. Here's how one might metaphorically or symbolically relate Quranic verses to the concepts of elementary particles and fundamental forces. Elementary particles in the Quran. Creation from water. Verse. Quran 21:30. Have not those who disbelieve considered that the heavens and the earth were a joined entity, and then we separated them and made from water every living thing? Interpretation. This verse might be seen to allude to the fundamental components of life, which at a basic level involve hydrogen and oxygen, water. While not directly about particles, it touches on the idea of fundamental elements from which all things are made. The smallest scale of matter. Verse Quran 34:3. But those who disbelieve say, "The hour will not come to us." Say, "Yes, by my Lord, it will surely come to you. Allah is the knower of the unseen." Not absent from him is an atom's weight within the heavens or within the earth, or what is smaller than that or greater, except that it is in a clear register. Interpretation. The mention of an atom's weight, and what's smaller than that, might be metaphorically linked to the idea of particles smaller than atoms, like quarks and leptons, although this is a very broad interpretation. Forces of nature in the Quran. Gravity and holding the heavens. Verse, Quran 13:2. Allah is the one who raised the heavens without any pillars that you can see. Then he established himself above the throne, and he subjected the sun and the moon, each running its course for a specified term. Interpretation. The concept of holding up the heavens without visible support can be seen as an ancient way of describing gravity, which holds celestial bodies in place without visible means. Electromagnetic forces. Verse Quran 36:40. It is not for the sun to overtake the moon, nor does the night outstrip the day. They all float, each in an orbit. Interpretation. This could be seen as an acknowledgement of the forces that keep celestial bodies in their orbits, where electromagnetic forces play a role in the stability of these systems. Weak and strong nuclear forces. Verse, Quran 67:3. He created 7 heavens, one above another. You do not see, in the creation of the Most Merciful, any inconsistency. So return your vision to the sky. Do you see any breaks? Interpretation. The layered nature of heavens might symbolically represent the complex interactions of forces at different scales, where the strong force binds quarks into protons and neutrons, and the weak force governs radioactive decay, both crucial for the structure of matter, balance and order. Verse Quran 55:7. And the heaven he raised and imposed the balance. Interpretation. The balance could be seen as a reference to the fundamental forces that keep the universe in equilibrium, where each force has its role in maintaining the order of creation. Philosophical and spiritual parallels. Unity of creation. The Quranic emphasis on the unity of God, Tawheed, can resonate with the idea of a unified theory in physics, where all forces and particles are aspects of one underlying reality. Signs in nature. The Quran repeatedly invites reflection on the signs in the heavens and the earth, encouraging a scientific curiosity that aligns with the exploration of particles and forces. Divine knowledge. Verses like Quran 6:59 suggest that Allah knows the minutest details of the universe, which can be metaphorically linked to the idea that all physical laws and particles are part of a grand design known only to the Creator. Caveats. Interpretation. These are metaphorical or symbolic interpretations. The Quran's primary aim is spiritual guidance, not scientific explanation. Any attempt to align Quranic texts with modern science should be done cautiously, respecting the text's original context and purpose. Cultural and historical context. The Quran was revealed in a 7th century Arabian context, where the language and symbolism used would resonate with the understanding of the time, not with modern scientific terminology. Diversity in thought. Within Islamic scholarship, there's a wide range of interpretations, with some scholars advocating for a separation between religious texts and scientific inquiry, while others see harmony or even predictive capacity in Quranic descriptions. This exploration shows how one might creatively interpret Quranic verses in light of modern physics, but it's crucial to acknowledge that these interpretations are not definitive scientific explanations, but rather reflections on the compatibility or symbolic resonance between religious text and scientific discovery. Continuing from the previous exploration, here are additional reflections on how the Quran might be metaphorically or symbolically linked to concepts in modern physics. Cosmic scale and time expansion of the universe. Verse, Quran 51:47. And the heaven we constructed with strength, and indeed we are its expander. Interpretation. This verse has been interpreted by some to reflect the modern understanding of the universe's expansion, a key concept in cosmology post-Big Bang. Time and relativity. Verse, Quran 22:47. And they urge you to hasten the punishment, but Allah will never fail in His promise. And indeed, a day with your Lord is like 1,000 years of those which you count. Interpretation. While primarily a spiritual teaching about patience and divine timing, this and similar verses, like 70.4, could metaphorically align with the concept of time dilation in relativity, where time's passage can be significantly different under various conditions or from different perspectives. Nature of existence. Creation from nothing. Verse Book Quran 2:117. The originator of the heavens and the earth. When he decrees a matter, he only says to it, "Be," and it is. Interpretation. This could be seen as a poetic expression of the idea that matter and energy came into existence from a state where they didn't previously exist, somewhat akin to the Big Bang theory where time and space began. Quantum mechanics and potentiality. Verse Quran 22:6. That is because Allah is the truth, and that what they call upon other than Him is falsehood, and because Allah is the Most High, the Grand. Interpretation. While not directly about physics, the concept of Allah as the truth might resonate with the quantum idea that all possibilities exist until observed, where truth or reality manifests from potentiality, akin to the wave function collapse. Interaction and harmony balance in nature. Verse Quran 16:7. And your Lord inspired to the bee, take for yourself among the mountains, houses, and among the trees and that which they construct. Interpretation. This could be seen as an acknowledgement of the intricate balance and interdependence in nature, where forces like gravity, electromagnetism, and biological processes work in harmony, reflecting the balance of forces in the quantum and classical realms. Duality and complementarity. Verse Quran 57:3. He is the first and the last, the ascendant and the intimate, and He is, of all things, knowing. Interpretation. The dual aspects of God described here might echo the wave-particle duality in quantum mechanics, where entities have both particle and wave-like properties, illustrating a complementary understanding of reality. Moral and ethical dimensions. Responsibility for knowledge. Verse Quran 2:30. And mention, O Muhammad, when your Lord said to the angels, Indeed, I will make upon the earth a successive authority. They said, Will you place upon it one who causes corruption therein and sheds blood, while we declare your praise and sanctify you? Allah said, Indeed, I know that which you do not know. Interpretation. This can be seen as an ethical charge to use the knowledge of the natural world, including physics, responsibly, acknowledging the potential for both good and harm. Limitations and reflections. Symbolism over literalism. The Quran employs a lot of metaphor, symbolism, and allegory. Modern scientific interpretation should be approached with an understanding that these are not literal scientific claims, but reflections on the wonder and order of creation. Open to interpretation. Islamic scholars have historically interpreted these verses in diverse ways, focusing more on spiritual and moral guidance than on scientific detail. Encouragement for inquiry. The Quran encourages contemplation of the universe as a means to understand the Creator, which aligns with the scientific endeavor to explore and understand the fundamental nature of reality. In this way, while the Quran does not provide a scientific treatise on elementary particles or forces, its verses can inspire or resonate with scientific thought through their themes of creation, balance, unity, and the encouragement to reflect on the signs of God in the natural world. Here are further considerations linking Quranic themes to modern physics, focusing on the philosophical and metaphysical implications. The concept of nothingness and creation. Ex nihilo creation. Verse Quran 1967. Does man not remember that we created him before when he was nothing? Interpretation. This touches upon the concept of creation from nothingness, which resonates with the scientific idea of the universe emerging from a singularity or quantum vacuum state, where nothing might be understood in a different context than total absence. Multidimensionality and universes, multiple heavens and earths. Verse Quran 65:12. Allah is He who created 7 heavens, and of the earth the like thereof. His command descends between them, that you may know that Allah is able to do all things. and that Allah surrounds all things in His knowledge. Interpretation. The notion of multiple heavens and earths could be metaphorically or symbolically linked to the modern concepts of parallel universes or different dimensions in string theory, where each heaven or earth represents a different plane or aspect of reality. The nature of light. Light as a symbol. Verse, Quran 24:35. Allah is the light of the heavens and the earth. The example of His light is like a niche within which is a lamp. The lamp is within glass. The glass as if it were a pearly white star lit from the oil of a blessed olive tree, neither of the east nor of the west, whose oil would almost glow even if untouched by fire. Light upon light. Allah guides to His light whom He wills. And Allah presents examples for the people, and Allah is knowing of all things. Interpretation. This verse, while primarily symbolic, might resonate with the dual nature of light in physics, as both a particle, photon, and a wave, and the complexity of light in quantum mechanics, where entanglement and superposition play roles. The quantum nature of reality, unseen and quantum entanglement. Verse, Quran 35:45. And if Allah were to punish people for what they earned, He would not leave upon the earth any creature, but He defers them for a specified term. And when their time comes, then indeed Allah has ever been, of His servants, seeing. Interpretation. The omnipresence and omniscience of God could be seen as analogous to the non-locality in quantum mechanics, where particles can be correlated across vast distances, reflecting a kind of cosmic interconnectedness. The role of consciousness, observation, and reality. Verse, Quran 50:16. And we have already created man and know what his soul whispers to him, and we are closer to him than his jugular vein. Interpretation. This could be metaphorically linked to the observer effect in quantum mechanics, where the act of observation affects the observed system, suggesting a deep connection between consciousness, observation, and the nature of reality. Ethical implications. Purpose and stewardship. Verse, Quran 2:30. And mention, O Muhammad, when your Lord said to the angels, Indeed, I will make upon the earth a successive authority. They said, Will you place upon it one who causes corruption therein and sheds blood, while we declare your praise and sanctify you? Allah said, Indeed, I know that which you do not know. Interpretation. This can be seen as a call to use scientific knowledge, including understanding of particles and forces, for the betterment of the world, highlighting the responsibility of humans as stewards of creation. Final thoughts. Integration of science and spirituality. The Quran's approach often integrates the observation of nature with spiritual reflection, encouraging believers to see the natural world as a testament to divine order and wisdom. Interpretative caution. While these connections can be intriguing, it's critical to maintain a distinction between the Quranic text's primary spiritual and moral guidance and the speculative nature of these scientific parallels. Encouragement for discovery. The Quran repeatedly invites contemplation of the universe, suggesting that the pursuit of knowledge, including scientific inquiry, is a form of worship and a path to understanding God's creation. In essence, these reflections highlight the potential for dialogue between Islamic theology and modern science, where each can inform and enrich the understanding of the other, while respecting their distinct domains and purposes. 0. Continuing our exploration of parallels between Quranic verses and modern physics, particularly focusing on the philosophical, metaphysical, and ethical dimensions. The concept of time, non-linear time. Verse Bishoy. Quran 74. The angels and the Spirit will ascend to him during a day the extent of which is 50,000 years. In interpretation, this verse might be seen in the light of relativity's concept of time dilation, where the experience of time can vary greatly depending on conditions like velocity or gravity. It could also suggest a more spiritual understanding of time, where divine time operates on a scale vastly different from human perception. Causality and determinism. Divine will and quantum indeterminacy. Verse, Quran 76:3. Indeed, we guided him to the way, be he grateful or be he ungrateful. Interpretation. This verse speaks to the divine guidance and human free will, which can be reflected in the quantum world where outcomes are probabilistic rather than deterministic, suggesting a universe where both divine will and human choice have a role. Symmetry and beauty in creation. Symmetry in nature. Verse, Quran 67:3. He created 7 heavens, one above another. You do not see in the creation of the most merciful any inconsistency. So return your vision to the sky. Do you see any breaks? Interpretation. The emphasis on no inconsistency in creation can be linked to the beauty and symmetry found in fundamental physics, from the symmetry of particle physics to the elegant equations of general relativity, where the universe's laws are seen as a manifestation of divine harmony. The concept of void and vacuum and potentiality. Verse, Quran 52:35. Or were they created by nothing, or were they the creators of themselves? Interpretation. This verse might resonate with the concept of the quantum vacuum, not as an empty space, but as a sea of potential energy and virtual particles from which creation can emerge, paralleling the notion of creation from nothing in a physical sense. Ethics of knowledge and power, responsibility with knowledge. 1 Quran 28:77. But seek, through that which Allah has given you, the home of the hereafter, and yet do not forget your share of the world, and do good as Allah has done good to you, and desire not corruption in the land. Indeed, Allah does not like corrupters. Interpretation. This can be seen as an ethical guide for scientists and technologists, reminding them that with great knowledge comes the responsibility to use it for the betterment of life, not for destruction or corruption. Interconnectedness. Unity of all things. Verse Key Quran 3:103. And hold firmly to the rope of Allah altogether, and do not become divided. Interpretation. This metaphor of the rope of Allah can be seen as a symbol of the interconnectedness of all things, akin to the entanglement in quantum mechanics or the holistic view of the universe in general relativity, where everything is part of an intricately woven fabric. Conclusion and reflections. Harmonious coexistence. The idea is not to claim that the Quran predicted modern physics, but to highlight how its teachings can resonate with scientific discoveries in a way that encourages awe, respect, and ethical responsibility towards creation. Mystical and scientific inquiry. Both the mystical tradition of Islam, Sufism, and science seek to understand the nature of reality, albeit through different lenses. The Quran might inspire a view of science not just as a means to understand the universe, but as part of a larger quest for truth and beauty in creation. Continuous learning. The Quranic call for reflection and study of the universe encourages an ongoing dialogue between faith and science, where each can enhance the understanding of the other without one needing to supplant the other. This exploration underscores the potential for a rich interaction between Islamic teachings and contemporary science, where the spiritual and the material are seen not as opposing, but as complementary aspects of understanding the world and our place in it. Here's a further exploration of how Quranic themes might be reflected in or resonate with concepts from modern physics, focusing on the metaphysical, existential, and ethical dimensions, the nature of reality. Manifestation from the unseen. Verse Quran 6:38. And there is no creature on or within the earth or bird that flies with its wings, except that they are communities like you. We have not neglected in the register a thing. Then unto their Lord they will be gathered. Interpretation. This could be likened to the concept of particles emerging from fields or the quantum vacuum, where the unseen, quantum fields, give rise to the seen, particles, reflecting a deeper layer of reality not directly observable. The unity of God and the unity of science. Tawhid and unified theories. Verse, Quran 12:1-4. Say, He is Allah, who is one, Allah, the eternal refuge. He neither begets nor is born, nor is there to him any equivalent. Interpretation. The concept of Tawhid, the oneness of God, might resonate with the search for a unified theory in physics, where all forces and particles are seen as aspects of one underlying reality. This unity in theology could inspire the unity sought in scientific theories, like the grand unified theory or the theory of everything. Life and quantum biology. Life from water and quantum effects. Verse, Quran 21:30. Have not those who disbelieve considered that the heavens and the earth were a joined entity, and then we separated them and made from water every living thing? Interpretation. Water here not only symbolizes life, but can also be linked to the quantum phenomena in biological systems, where water's unique properties at the molecular level might play roles in life processes, reflecting the complexity and interdependence of life at a fundamental level. The ethics of discovery. Seeking knowledge for good. Verse, Quran 3:190-191. Indeed, in the creation of the heavens and the earth and the alternation of the night and the day are signs for those of understanding, who remember Allah while standing or sitting or lying on their sides and give thought to the creation of the heavens and the earth, saying, Our Lord, you did not create this aimlessly. Exalted are you above such a thing. Then protect us from the punishment of the fire. Interpretation. This encourages the pursuit of knowledge with an ethical perspective, where understanding the universe is not just for curiosity or power, but for spiritual growth and the betterment of society, aligning with the idea that science should serve humanity's welfare. The concept of balance. Cosmic and moral balance. Verse, Quran 55:7-9. And the heaven. He raised and imposed the balance, that you not transgress within the balance, and establish weight in justice and do not make deficient the balance. Interpretation. The balance in the heavens can be seen as reflecting the balance of forces in the cosmos, gravity, electromagnetic, weak and strong forces, while also urging moral and ethical balance in human endeavors, including how we apply scientific knowledge. The eternal and the temporal eternal laws and changing nature. Verse Quran 35:43. Through pride, they the disbelievers behave insolently in the land and plot evil. But the evil plot does not encompass except its own people. Then do they await except the way of the former peoples. But you will never find in the way of Allah any change, and you will never find in the way of Allah any alteration. Interpretation. This could be seen as an acknowledgement of the unchanging laws of physics, the way of Allah, amidst the changing and evolving universe, suggesting that while the universe evolves, the underlying principles remain constant. Reflection on human role, stewardship, and inquiry. Verse, Quran 2:30. And mention, O Muhammad, when your Lord said to the angels, Indeed, I will make upon the earth a successive authority. They said, Will you place upon it one who causes corruption therein and sheds blood while we declare your praise and sanctify you? Yet Allah said, Indeed, I know that which you do not know. Interpretation. This places humans as stewards of Earth, with the responsibility to use scientific understanding for positive ends, reflecting on the dual potential of knowledge to either elevate or degrade. These reflections attempt to draw a bridge between the spiritual insights of the Quran and the material explorations of science, promoting a worldview where science and spirituality can coexist and even enrich each other, focusing on the wonder of creation and the ethical use of knowledge. Here's an additional layer of exploration on how Quranic themes might resonate with or inspire reflections on modern physics, focusing on deeper philosophical and existential questions. The nature of consciousness. Consciousness and the divine. Verse, Quran 50:16. And we have already created man, and know what his soul whispers to him, and we are closer to him than his jugular vein. Interpretation. This verse can evoke discussions in physics about consciousness and its relation to the physical world, particularly in contexts like the observer effect in quantum mechanics, where consciousness might play a role in the realization of physical states. It also speaks to the intimate connection between the creator and creation, potentially paralleling concepts like panpsychism in modern philosophy of mind. The concept of infinity. Infinite knowledge and infinite universe. Verse, Quran 31:27. And if whatever trees upon the earth were pens, and the sea was ink, replenished thereafter by 7 more seas, the words of Allah would not be exhausted. Indeed, Allah is exalted in might and wise. Interpretation. This could be seen as a poetic expression of infinity, paralleling the infinite nature of the universe in some cosmological models, or the infinite potential of quantum fields, where the vastness of knowledge or creation is beyond human comprehension. The mystery of the unseen realms and quantum uncertainty. Verse, Quran 35:18. And no bearer of burdens will bear the burden of another. And if a heavily laden soul calls another to carry some of its load, nothing of it will be carried, even if he should be a close relative. You can only warn those who fear their Lord unseen and have established prayer. And whoever purifies himself only purifies himself for the benefit of his soul, and to Allah is the final destination. Interpretation. The unseen here might resonate with the quantum realm, where much of reality is not directly observable, but influences the physical world, suggesting layers of reality beyond our perception, akin to spiritual dimensions or moral accountability beyond physical existence. Transcendence and immanence. God's presence everywhere. Verse Quran 57:4. He is with you wherever you are, and Allah is seeing of what you do. Interpretation. This could reflect on the concept of non-locality in quantum mechanics, or the omnipresence of fundamental forces like gravity, where the divine or the laws of physics are present everywhere, transcending yet immanent in all creation. The ethics of scientific inquiry. Knowledge for humility and service. Verse, Quran 2:269. He grants wisdom to whom he pleases, and he to whom wisdom is granted receives indeed a benefit overflowing. But none, remember, will receive admonition, except men of understanding. Interpretation. Wisdom here is not just intellectual knowledge, but encompasses ethical and spiritual understanding. This can be seen as a reminder for scientists to approach their work with humility, recognizing the vastness of what is unknown and using their knowledge to serve humanity rather than for personal gain or destruction. The purpose of creation. Creation with purpose. Verse, Quran 3:191. Those who remember Allah while standing, sitting, and lying on their sides, and reflect upon the creation of the heavens and the earth, saying, Our Lord, you did not create this aimlessly. Exalted are you above such a thing. Then protect us from the punishment of the fire. Interpretation. This encourages reflection on the purpose behind the universe's creation, aligning with the scientific quest for understanding not just how things work, but why they exist, fostering a sense of wonder and responsibility towards the cosmos. Final reflections dialogue between science and faith. This exploration isn't to suggest that the Quran is a scientific text, but rather to show how its verses can inspire philosophical questions about the nature of reality, the role of humans in the universe, and the ethical implications of scientific discovery. Harmony of knowledge. The Quranic emphasis on signs, ayat, in nature invites a harmonious view where scientific discovery is seen as part of recognizing and appreciating the Creator's work, fostering an environment where science and spirituality can complement each other. Encouragement for exploration. The Quran's invitation to ponder over creation encourages ongoing scientific inquiry, suggesting that each discovery is another step in understanding the vastness and beauty of the universe, always in the context of a greater purpose and responsibility. This approach highlights how ancient texts can inspire contemporary thought, urging us to consider the ethical, existential, and spiritual dimensions of our scientific endeavors. From time immemorial, humanity has gazed upon the world with an insatiable curiosity. Ancient Greek philosophers proposed basic elements, earth, air, fire, and water, as the building blocks of matter. These elements combined in various proportions to create the substances we observe. Aristotle elaborated on this concept. He proposed gravity and levity as fundamental forces. These early ideas laid the groundwork for understanding matter and its interactions. During the Renaissance, the concept of atoms resurfaced. Democritus proposed indivisible particles called atoms. In the 17th century, Robert Boyle revived atomic theory, proposing matter was composed of tiny particles. This marked a shift from philosophy to empirical science. The stage was set for a revolution in understanding the universe's building blocks. The 19th century witnessed significant strides in atomic theory, thanks to John Dalton, an English chemist and physicist. Dalton proposed a comprehensive and quantitative atomic theory. In 1808, he published a new system of chemical philosophy. Dalton's theory posited that all matter is composed of tiny, indivisible particles called atoms. Atoms of a given element are identical, while atoms of different elements have different masses and properties. Dalton proposed that chemical reactions involve the rearrangement of atoms. His work paved the way for a new era of scientific inquiry. The late 19th and early 20th centuries witnessed a series of groundbreaking discoveries that shattered the notion of atoms as indivisible particles. Physicists began to probe the atom's internal structure, revealing a subatomic world far more complex than previously imagined. The first hint of the atom's internal structure came with the discovery of the electron in 1897 by J.J. Thomson, a British physicist. Thomson's experiments with cathode rays, beams of negatively charged particles, led him to conclude that these particles, later named electrons, were fundamental constituents of all atoms. This discovery challenged Dalton's view of the atom as an indivisible entity, suggesting that atoms were, in fact, composed of smaller particles. In 1911, Ernest Rutherford, a New Zealand-born physicist, conducted his famous gold foil experiment, which provided further insights into the atom's structure. By bombarding a thin gold foil with alpha particles, positively charged particles, Rutherford observed that most of the alpha particles passed through the foil with little or no deflection, while a small fraction were deflected at large angles. The dawn of the 20th century marked a turning point in our understanding of the universe with the advent of quantum mechanics, a revolutionary theory that challenged the very foundations of classical physics. The development of quantum mechanics was driven by a series of perplexing experimental observations that could not be explained by classical physics, which had reigned supreme for centuries. One of the most significant contributions of quantum mechanics was the realization that energy, like matter, is quantized, meaning it exists in discrete packets called quanta. This revolutionary concept, first proposed by Max Planck in 1900, explained the observed spectrum of blackbody radiation, which had puzzled physicists for years. Planck's work laid the foundation for the development of quantum theory. In 1905, Albert Einstein, a young patent clerk at the time, published his groundbreaking paper on the photoelectric effect, which provided further evidence for the quantization of energy. Einstein proposed that light, which had been previously understood as a wave, could also behave as a stream of particles called photons, each carrying a discrete amount of energy. Section 5. Delving deeper, the elusive world of quarks. As physicists delved deeper into the structure of matter, they encountered a new class of particles called quarks, the fundamental building blocks of protons, neutrons, and other subatomic particles. The existence of quarks was first proposed in 1964 by Murray Gell-Mann and George Zweig, who independently developed the quark model. The quark model proposed that protons and neutrons are not fundamental particles, but are composed of even smaller particles called quarks. Initially, 3 types of quarks were proposed: up, down, and strange. Each quark was assigned a fractional electric charge, a property that distinguished them from other known particles. The up quark has a charge of plus 2/3, the down quark has a charge of minus 1/3, and the strange quark has a charge of minus 1/3. According to the quark model, a proton is composed of 2 up quarks and 1 down quark, giving it a net charge of plus 1. A neutron, on the other hand, is composed of 1 up quark and 2 down quarks, resulting in a net charge of 0. The quark model elegantly explained the observed properties of protons, neutrons, and other subatomic particles, providing a unified framework for understanding the structure of matter at its most fundamental level. Section 6. The strong force holding the nucleus together. In the realm of particle physics, the strong force reigns supreme as the most powerful of the four fundamental forces of nature. This force is responsible for binding quarks together to form protons and neutrons, as well as holding the nucleus of an atom together, overcoming the immense electrostatic repulsion between positively charged protons. The strong force exhibits peculiar characteristics that set it apart from other fundamental forces. Its strength increases with distance, acting like a subatomic rubber band. The more you try to pull quarks apart, the stronger the force becomes. However, beyond a critical distance, roughly the size of a proton, the strong force rapidly diminishes, explaining why quarks are confined within protons and neutrons. Mediating this powerful force are particles called gluons, aptly named for their role in gluing quarks together. Gluons are massless, chargeless particles that constantly interact with quarks, exchanging energy and momentum, thereby holding the nucleus together. The strong force plays a crucial role in the stability of matter, ensuring the existence of atoms and, consequently, the universe as we know it. Without the strong force, protons would repel each other, causing atomic nuclei to disintegrate, and the universe would be a vastly different place. Section 7. The weak force. A force of change and transformation. The weak force, though less powerful, is crucial in shaping the universe. It governs the transformation of quarks, known as quark flavor change. Responsible for radioactive decay, it helps unstable nuclei become stable. In beta decay, a neutron becomes a proton, electron, and antineutrino. The weak force is vital in stellar nucleosynthesis, forging heavier elements. Without it, stars couldn't produce elements needed for life. Section 8. Electromagnetism. The force we experience every day. The electromagnetic force, a fundamental force of nature, governs the interactions between electrically charged particles. It is responsible for a wide range of phenomena we experience every day, from the attraction and repulsion of magnets to the behavior of light and other electromagnetic radiation. The electromagnetic force manifests itself in two seemingly distinct but interconnected ways: electricity and magnetism. Electricity arises from the presence of stationary electric charges, while magnetism is associated with moving electric charges. However, these two phenomena are intimately intertwined, as a moving electric charge creates a magnetic field, and a changing magnetic field induces an electric current. This interplay between electricity and magnetism is beautifully described by Maxwell's equations, a set of four equations that unified electricity, magnetism, and optics into a single, elegant framework. The electromagnetic force is mediated by photons, massless, chargeless particles that travel at the speed of light. Photons are the quanta of electromagnetic radiation, carrying energy and momentum. They are responsible for transmitting the electromagnetic force between charged particles, influencing their motion and interactions. Section 9. Gravity, the architect of the cosmos. Gravity, the weakest of the four fundamental forces, reigns supreme on astronomical scales, shaping the large-scale structure of the universe. It is the force responsible for the formation of stars, planets, and galaxies, holding these celestial objects in their cosmic dance. Unlike the other fundamental forces, gravity is always attractive, drawing massive objects toward each other. The strength of the gravitational force between two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Despite its weakness at the atomic and subatomic levels, gravity's influence is pervasive on astronomical scales. It is the architect of the cosmos, shaping the distribution of matter and energy throughout the universe. The search for a quantum theory of gravity, one that can reconcile gravity with the other fundamental forces at the quantum level, remains one of the most significant challenges in modern physics. Such a theory would provide a unified framework for understanding the universe at its most fundamental level: elementary particles and the forces of nature. Aristotle believed that all the matter in the universe was made up of four basic elements: earth, air, fire, and water. These elements were acted on by two forces: gravity, the tendency for earth and water to sink, and levity, the tendency for air and fire to rise. This division of the contents of the universe into matter and forces is still used today. Aristotle believed that matter was continuous. That is, one could divide a piece of matter into smaller and smaller bits without any limit. One never came up against a grain of matter that could not be divided further. A few Greeks, however, such as Democritus, held that matter was inherently grainy and that everything was made up of large numbers of various different kinds of atoms. The word atom means indivisible in Greek. For centuries, the argument continued without any real evidence on either side. But in 1803, the British chemist and physicist John Dalton pointed out that the fact that chemical compounds always combined in certain proportions could be explained by the grouping together of atoms to form units called molecules. However, the argument between the two schools of thought was not finally settled in favor of the atomists until the early years of this century. One of the important pieces of physical evidence was provided by Einstein. In a paper written in 1905, a few weeks before the famous paper on special relativity, Einstein pointed out that what was called Brownian motion, the irregular random motion of small particles of dust suspended in a liquid, could be explained as the effect of atoms of the liquid colliding with the dust particles. By this time, there were already suspicions that these atoms were not, after all, indivisible. Several years previously, a fellow of Trinity College, Cambridge, J.J. Thomson, had demonstrated the existence of a particle of matter, called the electron, that had a mass less than 1,000th of that of the lightest atom. He used a setup rather like a modern TV picture tube. A red-hot metal filament gave off the electrons. And because these have a negative electric charge, an electric field could be used to accelerate them toward a phosphor-coated screen. When they hit the screen, flashes of light were generated. Soon it was realized that these electrons must be coming from within the atoms themselves. And in 1911, the New Zealand physicist Ernest Rutherford finally showed that the atoms of matter do have internal structure. They are made up of an extremely tiny, positively charged nucleus, around which a number of electrons orbit. He deduced this by analyzing the way in which alpha particles, which are positively charged particles given off by radioactive atoms, are deflected when they collide with atoms. At first, it was thought that the nucleus of the atom was made up of electrons and different numbers of a positively charged particle called the proton, from the Greek word meaning first, because it was believed to be the fundamental unit from which matter was made. However, in 1932, a colleague of Rutherford's at Cambridge, James Chadwick, discovered that the nucleus contained another particle, called the neutron, which had almost the same mass as a proton, but no electrical charge. Chadwick received the Nobel Prize for his discovery and was elected Master of Gonville and Caius College, Cambridge, the college of which I am now a fellow. He later resigned as master because of disagreements with the fellows. There had been a bitter dispute in the college ever since a group of young fellows returning after the war had voted many of the old fellows out of the college offices they had held for a long time. This was before my time. I joined the college in 1965 at the tail end of the bitterness, when similar disagreements forced another Nobel Prize, winning master, Sir Neville Mott, to resign. Up to about 30 years ago, it was thought that protons and neutrons were elementary particles, but experiments in which protons were collided with other protons or electrons at high speeds indicated that they were in fact made up of smaller particles. These particles were named quarks by the Caltech physicist Murray Gell-Mann, who won the Nobel Prize in 1969 for his work on them. The origin of the name is an enigmatic quotation from James Joyce, 3 quarks for muster mark. The word quark is supposed to be pronounced like quart, but with a K at the end instead of a T, but is usually pronounced to rhyme with lark. There are a number of different varieties of quarks. There are 6 flavors, which we call up, down, strange, charmed, bottom, and top. The first 3 flavors had been known since the 1960s, but the charmed quark was discovered only in 1974, the bottom in 1977, and the top in 1995. Each flavor comes in 3 colors, red, green, and blue. It should be emphasized that these terms are just labels. Quarks are much smaller than the wavelength of visible light, and so do not have any color in the normal sense. It is just that modern physicists seem to have more imaginative ways of naming new particles and phenomena. They no longer restrict themselves to Greek. A proton or neutron is made up of 3 quarks, one of each color. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down and 1 up. We can create particles made up of the other quarks, strange, charmed, bottom, and top, but these all have a much greater mass and decay very rapidly into protons and neutrons. We now know that neither the atoms nor the protons and neutrons within them are indivisible. So the question is, what are the truly elementary particles, the basic building blocks from which everything is made? Since the wavelength of light is much larger than the size of an atom, we cannot hope to look at the parts of an atom in the ordinary way. We need to use something with a much smaller wavelength. As we saw in the last chapter, quantum mechanics tells us that all particles are in fact waves, and that the higher the energy of a particle, the smaller the wavelength of the corresponding wave. So the best answer we can give to our question depends on how high a particle energy we have at our disposal, because this determines on how small a length scale we can look. These particle energies are usually measured in units called electron volts. In Thomson's experiments with electrons, we saw that he used an electric field to accelerate the electrons. The energy that an electron gains from an electric field of 1 volt is what is known as an electron volt. In the 19th century, when the only particle energies that people knew how to use were the low energies of a few electron volts generated by chemical reactions such as burning, it was thought that atoms were the smallest unit. In Rutherford's experiment, the alpha particles had energies of millions of electron volts. More recently, we have learned how to use electromagnetic fields to give particles energies of at first millions and then thousands of millions of electron volts. And so we know that particles that were thought to be elementary 30 years ago are, in fact, made up of smaller particles. May these, as we go to still higher energies, in turn be found to be made from still smaller particles? This is certainly possible, but we do have some theoretical reasons for believing that we have, or are very near to, a knowledge of the ultimate building blocks of nature. Using the wave-particle duality discussed in the last chapter, everything in the universe, including light and gravity, can be described in terms of particles. These particles have a property called spin. One way of thinking of spin is to imagine the particles as little tops spinning about an axis. However, this can be misleading because quantum mechanics tells us that the particles do not have any well-defined axis. What the spin of a particle really tells us is what the particle looks like from different directions. A particle of spin 0 is like a dot. It looks the same from every direction. Figure 5.1i. On the other hand, a particle of spin 1 is like an arrow. It looks different from different directions. Figure 5.1.2. Only if one turns it round, a complete revolution, 360 degrees, does the particle look the same. A particle of spin 2 is like a double-headed arrow. Figure 5.1.3. It looks the same if one turns it round, half a revolution, 180 degrees. Similarly, higher spin particles look the same if one turns them through smaller fractions of a complete revolution. All this seems fairly straightforward, but the remarkable fact is that there are particles that do not look the same if one turns them through just 1 revolution. You have to turn them through 2 complete revolutions. Such particles are said to have spin Figure 5.1. All the known particles in the universe can be divided into 2 groups. Particles of spin 1 tau, which make up the matter in the universe, and particles of spin 0, 1, and 2, which, as we shall see, give rise to forces between the matter particles. The matter particles obey what is called Pauli's exclusion principle. This was discovered in 1925 by an Austrian physicist, Wolfgang Pauli, for which he received the Nobel Prize in 1945. He was the archetypal theoretical physicist. It was said of him that even his presence in the same town would make experiments go wrong. Pauli's exclusion principle says that 2 similar particles cannot exist in the same state. That is, they cannot have both the same position and the same velocity within the limits given by the uncertainty principle. The exclusion principle is crucial because it explains why matter particles do not collapse to a state of very high density under the influence of the forces produced by the particles of spin 0, 1, and 2. If the matter particles have very nearly the same positions, they must have different velocities, which means that they will not stay in the same position for long. If the world had been created without the exclusion principle, quarks would not form separate, well-defined protons and neutrons. Nor would these, together with electrons, form separate, well-defined atoms. They would all collapse to form a roughly uniform, dense soup. A proper understanding of the electron and other spin-half particles did not come until 1928, when a theory was proposed by Paul Dirac, who later was elected to the Lucasian Professorship of Mathematics at Cambridge, the same professorship that Newton had once held, and that I now hold. Dirac's theory was the first of its kind that was consistent with both quantum mechanics and the special theory of relativity. It explained mathematically why the electron had spin-half, that is, why it didn't look the same if you turned it through only one complete revolution, but did if you turned it through 2 revolutions. It also predicted that the electron should have a partner, an anti-electron or positron. The discovery of the positron in 1932 confirmed Dirac's theory and led to his being awarded the Nobel Prize for Physics in 1933. We now know that every particle has an antiparticle with which it can annihilate. In the case of the force-carrying particles, the antiparticles are the same as the particles themselves. There could be whole anti-worlds and anti-people made out of antiparticles. However, if you meet your anti-self, don't shake hands. You would both vanish in a great flash of light. The question of why there seem to be so many more particles than antiparticles around us is extremely important, and I shall return to it later in the chapter. In quantum mechanics, the forces or interactions between matter particles are all supposed to be carried by particles of integer spin, 0, 1, or 2. What happens is that a matter particle, such as an electron or a quark, emits a force-carrying particle. The recoil from this emission changes the velocity of the matter particle. The force-carrying particle then collides with another matter particle and is absorbed. This collision changes the velocity of the second particle, just as if there had been a force between the 2 matter particles. It is an important property of the force-carrying particles that they do not obey the exclusion principle. This means that there is no limit to the number that can be exchanged, and so they can give rise to a strong force. However, if the force-carrying particles have a high mass, it will be difficult to produce and exchange them over a large distance. So the forces that they carry will have only a short range. On the other hand, if the force-carrying particles have no mass of their own, the forces will be long range. The force-carrying particles exchanged between matter particles are said to be virtual particles because, unlike real particles, they cannot be directly detected by a particle detector. We know they exist, however, because they do have a measurable effect. They give rise to forces between matter particles. Particles of spin 0, 1, or 2 do also exist in some circumstances as real particles, when they can be directly detected. They then appear to us as what a classical physicist would call waves, such as waves of light or gravitational waves. They may sometimes be emitted when matter particles interact with each other by exchanging virtual force-carrying particles. For example, the electric repulsive force between 2 electrons is due to the exchange of virtual photons, which can never be directly detected. But if one electron moves past another, real photons may be given off, which we detect as light waves. Force-carrying particles can be grouped into 4 categories according to the strength of the force that they carry and the particles with which they interact. It should be emphasized that this division into 4 classes is man-made. It is convenient for the construction of partial theories, but it may not correspond to anything deeper. Ultimately, most physicists hope to find a unified theory that will explain all 4 forces as different aspects of a single force. Indeed, many would say this is the prime goal of physics today. Recently, successful attempts have been made to unify 3 of the 4 categories of force, and I shall describe these in this chapter. The question of the unification of the remaining category, gravity, we shall leave till later. The first category is the gravitational force. This force is universal. That is, every particle feels the force of gravity according to its mass or energy. Gravity is the weakest of the 4 forces by a long way. It is so weak that we would not notice it at all were it not for two special properties that it has. It can act over large distances, and it is always attractive. This means that the very weak gravitational forces between the individual particles in two large bodies, such as the Earth and the Sun, can all add up to produce a significant force. The other three forces are either short-range or are sometimes attractive and sometimes repulsive, so they tend to cancel out. In the quantum mechanical way of looking at the gravitational field, the force between two matter particles is pictured as being carried by a particle of spin 2, called the graviton. This has no mass of its own, so the force that it carries is long-range. The gravitational force between the Sun and the Earth is ascribed to the exchange of gravitons between the particles that make up these two bodies. Although the exchanged particles are virtual, they certainly do produce a measurable effect. They make the Earth orbit the Sun. Real gravitons make up what classical physicists would call gravitational waves, which are very weak, and so difficult to detect that they have not yet been observed. The next category is the electromagnetic force, which interacts with electrically charged particles like electrons and quarks, but not with uncharged particles such as gravitons. It is much stronger than the gravitational force. The electromagnetic force between two electrons is about a million, one with 42 zeros after it, times bigger than the gravitational force. However, there are two kinds of electric charge, positive and negative. The force between two positive charges is repulsive, as is the force between two negative charges, but the force is attractive between a positive and a negative charge. A large body, such as the Earth or the Sun, contains nearly equal numbers of positive and negative charges. Thus, the attractive and repulsive forces between the individual particles nearly cancel each other out, and there is very little net electromagnetic force. However, on the small scales of atoms and molecules, electromagnetic forces dominate. The electromagnetic attraction between negatively charged electrons and positively charged protons in the nucleus causes the electrons to orbit the nucleus of the atom, just as gravitational attraction causes the Earth to orbit the Sun. The electromagnetic attraction is pictured as being caused by the exchange of large numbers of virtual massless particles of spin 1, called photons. Again, the photons that are exchanged are virtual particles. However, when an electron changes from one allowed orbit to another, one nearer to the nucleus, energy is released and a real photon is emitted, which can be observed as visible light by the human eye, if it has the right wavelength, or by a photon detector such as photographic film. Equally, if a real photon collides with an atom, it may move an electron from an orbit nearer the nucleus to one farther away. This uses up the energy of the photon, so it is absorbed. The third category is called the weak nuclear force, which is responsible for radioactivity, and which acts on all matter particles of spin eta Honsel, but not on particles of spin 0, 1, or 2, such as photons and gravitons. The weak nuclear force was not well understood until 1967, when Abdus Salam at Imperial College London and Steven Weinberg at Harvard both proposed theories that unified this interaction with the electromagnetic force, just as Maxwell had unified electricity and magnetism about 100 years earlier. They suggested that in addition to the photon, there were three other spin 1 particles, known collectively as massive vector bosons, that carried the weak force. These were called W+, pronounced W+, W, pronounced W-, and ZO, pronounced Z0, and each had a mass of around 100 GeV. GeV stands for giga-electron volt, or 1,000 million electron volts. The Weinberg-Salam theory exhibits a property known as spontaneous symmetry breaking. This means that what appear to be a number of completely different particles at low energies are in fact found to be all the same type of particle, only in different states. At high energies, all these particles behave similarly. The effect is rather like the behavior of a roulette ball on a roulette wheel. At high energies, when the wheel is spun quickly, the ball behaves in essentially only one way. It rolls round and round. But as the wheel slows, the energy of the ball decreases, and eventually the ball drops into one of the 37 slots in the wheel. In other words, at low energies, there are 37 different states in which the ball can exist, If, for some reason, we could only observe the ball at low energies, we would then think that there were 37 different types of ball. In the Weinberg-Salam theory, at energies much greater than 100 GeV, the three new particles and the photon would all behave in a similar manner. But at the lower particle energies that occur in most normal situations, this symmetry between the particles would be broken. We, W, and ZO would acquire large masses, making the forces they carry have a very short range. At the time that Salam and Weinberg proposed their theory, few people believed them, and particle accelerators were not powerful enough to reach the energies of 100 GeV required to produce real W+, W, or ZO particles. However, over the next 10 years or so, the other predictions of the theory at lower energies agreed so well with experiment that, in 1979, Salam and Weinberg were awarded the Nobel Prize for Physics, together with Sheldon Glashow, also at Harvard, who had suggested similar unified theories of the electromagnetic and weak nuclear forces. The Nobel Committee was spared the embarrassment of having made a mistake by the discovery in 1983 at CERN, European Center for Nuclear Research, of the three massive partners of the photon, with the correct predicted masses and other properties. Carlo Rubbia, who led the team of several hundred physicists that made the discovery, received the Nobel Prize in 1984, along with Simon Vandermeer, the CERN engineer who developed the antimatter storage system employed. It is very difficult to make a mark in experimental physics these days, unless you are already at the top. The fourth category is the strong nuclear force, which holds the quarks together in the proton and neutron, and holds the protons and neutrons together in the nucleus of an atom. It is believed that this force is carried by another spin-1 particle, called the gluon, which interacts only with itself and with the quarks. The strong nuclear force has a curious property called confinement. It always binds particles together into combinations that have no color. One cannot have a single quark on its own because it would have a color, red, green, or blue. Instead, a red quark has to be joined to a green and a blue quark by a string of gluons. Red plus green plus blue equal white. Such a triplet constitutes a proton or a neutron. Another possibility is a pair consisting of a quark and an antiquark. Red plus anti-red, or green plus anti-green, or blue plus anti-blue equals white. Such combinations make up the particles known as mesons, which are unstable because the quark and antiquark can annihilate each other, producing electrons and other particles. Similarly, confinement prevents one having a single gluon on its own, because gluons also have color. Instead, one has to have a collection of gluons whose colors add up to white. Such a collection forms an unstable particle called a glue ball. The fact that confinement prevents one from observing an isolated quark or gluon might seem to make the whole notion of quarks and gluons as particles somewhat metaphysical. However, there is another property of the strong nuclear force, called asymptotic freedom, that makes the concept of quarks and gluons well defined. At normal energies, the strong nuclear force is indeed strong, and it binds the quarks tightly together. However, experiments with large particle accelerators indicate that at high energies, the strong force becomes much weaker, and the quarks and gluons behave almost like free particles. Figure 5.2. Figure 5.2 shows a photograph of a collision between a high-energy proton and antiproton. The success of the unification of the electromagnetic and weak nuclear forces led to a number of attempts to combine these two forces with the strong nuclear force into what is called a grand unified theory, or GUT. This title is rather an exaggeration. The resultant theories are not all that grand, nor are they fully unified, as they do not include gravity. Nor are they really complete theories, because they contain a number of parameters whose values cannot be predicted from the theory, but have to be chosen to fit in with experiment. Nevertheless, they may be a step toward a complete, fully unified theory. The basic idea of JUTs is as follows. As was mentioned above, the strong nuclear force gets weaker at high energies. On the other hand, the electromagnetic and weak forces, which are not asymptotically free, get stronger at high energies. At some very high energy, called the grand unification energy, these three forces would all have the same strength, and so could just be different aspects of a single force. The Gautés also predict that at this energy, the different spin-a-half matter particles, like quarks and electrons, would also all be essentially the same, thus achieving another unification. The value of the grand unification energy is not very well known, but it would probably have to be at least 1,000 million GeV. The present generation of particle accelerators can collide particles at energies of about 100 GeV, and machines are planned that would raise this to a few thousand GeV. But a machine that was powerful enough to accelerate particles to the grand unification energy would have to be as big as the solar system, and would be unlikely to be funded in the present economic climate. Thus, it is impossible to test grand unified theories directly in the laboratory. However, just as in the case of the electromagnetic and weak unified theory, there are low-energy consequences of the theory that can be tested. The most interesting of these is the prediction that protons, which make up much of the mass of ordinary matter, can spontaneously decay into lighter particles such as anti-electrons. The reason this is possible is that at the grand unification energy, there is no essential difference between a quark and an anti-electron. The three quarks inside a proton normally do not have enough energy to change into anti-electrons, but very occasionally, one of them may acquire file/C/Windows desktop. Blah. Stephen Hawking. A Brief History of Time. DHETL 6 of 8. 2. 20s. 2001. 3:14:54 a.m. A Brief History of Time. Stephen Hawking. Chapter 5. Sufficient energy to make the transition, because the uncertainty principle means that the energy of the quarks inside the proton cannot be fixed exactly. The proton would then decay. The probability of a quark gaining sufficient energy is so low that one is likely to have to wait at least a million years. 1 followed by 30 zeros. This is much longer than the time since the Big Bang, which is a mere 10,000 million years or so. 1 followed by 10 zeros. Thus, one might think that the possibility of spontaneous proton decay could not be tested experimentally. However, one can increase one's chances of detecting a decay by observing a large amount of matter containing a very large number of protons. If, for example, one observed a number of protons equal to 1 followed by 31 zeros for a period of 1 year, one would expect, according to the simplest Gauté, to observe more than 1 proton decay. A number of such experiments have been carried out, but none have yielded definite evidence of proton or neutron decay. One experiment used 8,000 tons of water and was performed in the Morton salt mine in Ohio, to avoid other events taking place, caused by cosmic rays, that might be confused with proton decay. Since no spontaneous proton decay had been observed during the experiment, one can calculate that the probable life of the proton must be greater than 10 million years, 1 with 31 zeros. This is longer than the lifetime predicted by the simplest grand unified theory, but there are more elaborate theories in which the predicted lifetimes are longer. Still more sensitive experiments involving even larger quantities of matter will be needed to test them. Even though it is very difficult to observe spontaneous proton decay, it may be that our very existence is a consequence of the reverse process, the production of protons, or more simply, of quarks, from an initial situation in which there were no more quarks than antiquarks, which is the most natural way to imagine the universe starting out. Matter on the Earth is made up mainly of protons and neutrons, which in turn are made up of quarks. There are no antiprotons or antineutrons made up from antiquarks, except for a few that physicists produce in large particle accelerators. We have evidence from cosmic rays that the same is true for all the matter in our galaxy. There are no antiprotons or antineutrons apart from a small number that are produced as particle/antiparticle pairs in high-energy collisions. If there were large regions of antimatter in our galaxy, we would expect to observe large quantities of radiation from the borders between the regions of matter and antimatter, where many particles would be colliding with their antiparticles, annihilating each other and giving off high-energy radiation. We have no direct evidence as to whether the matter in other galaxies is made up of protons and neutrons or antiprotons and antineutrons, but it must be one or the other. There cannot be a mixture in a single galaxy, because in that case, we would again observe a lot of radiation from annihilations. We therefore believe that all galaxies are composed of quarks rather than antiquarks. It seems implausible that some galaxies should be matter and some antimatter. Why should there be so many more quarks than antiquarks? Why are there not equal numbers of each? It is certainly fortunate for us that the numbers are unequal, because if they had been the same, nearly all the quarks and antiquarks would have annihilated each other in the early universe and left a universe filled with radiation, but hardly any matter. There would then have been no galaxies, stars, or planets on which human life could have developed. Luckily, grand unified theories may provide an explanation of why the universe should now contain more quarks than antiquarks, even if it started out with equal numbers of each. As we have seen, JUTs allow quarks to change into anti-electrons at high energy. They also allow the reverse processes, antiquarks turning into electrons, and electrons and anti-electrons turning into antiquarks and quarks. There was a time in the very early universe when it was so hot that the particle energies would have been high enough for these transformations to take place. But why should that lead to more quarks than antiquarks? The reason is that the laws of physics are not quite the same for particles and antiparticles. Up to 1956, it was believed that the laws of physics obeyed each of three separate symmetries called C, P, and T. The symmetry C means that the laws are the same for particles and antiparticles. The symmetry P means that the laws are the same for any situation and its mirror image. The mirror image of a particle spinning in a right-handed direction is one spinning in a left-handed direction. The symmetry T means that if you reverse the direction of motion of all particles and antiparticles, the system should go back to what it was at earlier times. In other words, the laws are the same in the forward and backward directions of time. In 1956, two American physicists, Tsung-Dao Lee and Chen-Ning Yang, suggested that the weak force does not in fact obey the symmetry P. In other words, the weak force would make the universe develop in a different way from the way in which the mirror image of the universe would develop. The same year, a colleague, Chien-Shung Wu, proved their prediction correct. She did this by lining up the nuclei of radioactive atoms in a magnetic field so that they were all spinning in the same direction, and showed that the electrons were given off more in one direction than another. The following year, Li and Yang received the Nobel Prize for their idea. It was also found that the weak force did not obey the symmetry C. That is, it would cause a universe composed of antiparticles to behave differently from our universe. Nevertheless, it seemed that the weak force did obey the combined symmetry CP. That is, the universe would develop in the same way as its mirror image if, in addition, every particle was swapped with its antiparticle. However, in 1964, two more Americans, J.W. Cronin and Val Fitch, discovered that even the CP symmetry was not obeyed in the decay of certain particles called K-mesons. Cronin and Fitch eventually received the Nobel Prize for their work in 1980. A lot of prizes have been awarded for showing that the universe is not as simple as we might have thought. There is a mathematical theorem that says that any theory that obeys quantum mechanics and relativity must always obey the combined symmetry CPT. In other words, the universe would have to behave the same if one replaced particles by antiparticles, took the mirror image, and also reversed the direction of time. But Cronin and Fitch showed that if one replaces particles by antiparticles and takes the mirror image, but does not reverse the direction of time, then the universe does not behave the same. The laws of physics, therefore, must change if one reverses the direction of time. They do not obey the symmetry T. Certainly the early universe does not obey the symmetry T. As time runs forward, the universe expands. If it ran backward, the universe would be contracting. And since there are forces that do not obey the symmetry T, it follows that as the universe expands, these forces could cause more anti-electrons to turn into quarks than electrons into antiquarks. Then, as the universe expanded and cooled, the antiquarks would annihilate with the quarks. But since there would be more quarks than antiquarks, a small excess of quarks would remain. It is these that make up the matter we see today, and out of which we ourselves are made. Thus, our very existence could be regarded as a confirmation of grand unified theories, though a qualitative one only. The uncertainties are such that one cannot predict the numbers of quarks that will be left after the annihilation, or even whether it would be quarks or antiquarks that would remain. Had it been an excess of antiquarks, however, we would simply have named antiquarks quarks and quarks antiquarks. Grand unified theories do not include the force of gravity. This does not matter too much, because gravity is such a weak force that its effects can usually be neglected when we are dealing with elementary particles or atoms. However, the fact that it is both long-range and always attractive means that its effects all add up. So for a sufficiently large number of matter particles, gravitational forces can dominate over all other forces. This is why it is gravity that determines the evolution of the universe. Even for objects the size of stars, the attractive force of gravity can win over all the other forces and cause the star to collapse. My work in the 1970s focused on the black holes that can result from such stellar collapse and the intense gravitational fields around them. It was this that led to the first hints of how the theories of quantum mechanics and general relativity might affect each other, a glimpse of the shape of a quantum theory of gravity yet to come. In exploring the connections between Quranic themes and modern physics, we've ventured into a dialogue where ancient spiritual insights meet contemporary scientific inquiry. This exploration is not about proving one by the other, but about illustrating how both can enrich our understanding of existence. Awe and wonder. The Quran's repeated calls to reflect on the signs in the heavens and the earth resonate with the scientific pursuit of understanding the universe's mysteries. Both encourage a sense of awe and wonder at creation, whether from a spiritual or scientific perspective. Unity and interconnectedness. Tawheed, the oneness of God, inspire the search for a unified physics, suggesting that beneath lies a profound unity. This unity of all things, from quantum entanglement to the cosmic ethical responsibility. The ethical dimensions in the Quran emphasize of society, a principle that aligns with the ethical considerations in how we apply discoveries like those in particle physics or the role of humility, both spiritual teachings and scientific human knowledge. The Quran's acknowledgement of the unseen and the vastness of divine science, where each answer often leads to new questions. Stewardship. The Quran's depiction of Earth encourages a responsible approach to exploration, urging us to consider the long-term impact and its inhabitants. Complementarity of knowledge. Science and spirituality, not as opposing forces, but we can foster a worldview where both can coexist into different aspects of the human experience and the nature of reality. This intersection of Quranic philosophy with modern physics invites us to pursue knowledge with reverence or experimentation. The quest for knowledge is seen as a noble endeavor in the mysteries of life and creation. Both the Quran and science acknowledge the vastness of the unknown. Acknowledgement can lead to a more profound appreciation for the universe's beauty. Live ethically. With great knowledge comes great responsibility in using their knowledge to promote peace, justice, and the well-being of all creation. This dialogue between the Quranic worldview and the scientific exploration of the cosmos doesn't resolve all conflicts or answer all questions, but instead opens new avenues for thought, where each discipline can inform and inspire the other. It's a reminder that in the pursuit of understanding, we are all, in some way, searching for the same truth, albeit through different lenses.